All right. Uh, Welcome everybody to the May 2026 version of the CFAS General Meeting. I am your host and president, Wesley Clem, and let's get this show on the road. All right. Uh, if you are watching this or catching it later on YouTube and you're not a member of CFAS, I encourage you to join. We have a lot of perks and benefits to joining. We have access to our private events and dark sky viewing locations. We have access to one of the darker skies around here in Orlando. So if you want to go out, try out equipment, and enjoy a nice dark sky and interact with other members of the club, it's a fun evening, I promise. We also have the Loner Telescope program and our remote observing program. We have loner telescopes in the club that you can check out and use and fiddle around with and get used to before, in a try before you buy sort of way. And we also have our remote observing program. We have a sea star out at a dark sky in Texas that you can remote into and use and see what it's like to actually do some astrophotography under a dark sky. It's a whole different animal than what you're used to in the city. We have our online community on our groups.io website. It's a great place to get together with other people in the club that are like-minded. You can ask questions, you can interact with other people, and it's also where all of our announcements are. So to find out about this meeting, information about our dark sky events, I encourage you to get on there and join us and interact with anybody and ask for help if you need it. We also have our quarterly meetings out at Seminole State's Planetarium. It's a fantastic place to have a club meeting, an astronomy club meeting. So it doesn't really get much better than that. You also get membership to the Astronomical League, and you'll receive your quarterly Reflector magazine. So that's also a great perk to being in this club. We're also a nonprofit 501c3 organization. We are all volunteers. None of us get paid, and all of everything that you contribute to the club goes to improving the club. You also get discounts on astronomy and sky and telescope magazines. So whether you're a new member or an existing member, if you're not taking advantage of that, be sure to do so. Tonight's agenda, we have Giovanni Lenguito giving a talk on space climatology and space weather. We then follow that by club news, upcoming events, and then finally our astrophotography showcase. So without further ado, I would like to introduce our speaker for tonight. Giovanni Lenguito is an expert in the field of aerospace engineering and space systems. He is currently a principal engineer at Airbus US Space and Defense, where he develops electric propulsion systems for satellite constellations, and he serves as subject matter expert in space environments. He previously developed and qualified propulsion components and systems that operate in LEO, GEO, and deep space. His technical depth is grounded in plasma physics and advanced satellite propulsion. He graduated from the University of Naples in Italy and achieved his PhD from Yale University in New Haven, Connecticut. He has conducted extensive research into electric propulsion and plasma physics, but also in microfluidic systems for biomedical applications. This very diverse background allows him to bridge the gap between theoretical physics and practical engineering. Giovanni, thank you so much for joining us tonight. And if it's okay, I'd like to toss it over to you and hear all about space climatology.
Thank you so much. Thanks for the introduction. It's a pleasure to be here with all of you. I'll start sharing my screen. Make sure I can get there. All right, hopefully I'm sharing.
There we go.
And cool. So yeah, thanks. Just to say, like, it's actually a pleasure to get to talk to you guys. I'm actually always been very interested myself in astronomy. I mean, as you can imagine, from my background, of course, all of us dreamed as kids to work with something up there. So it's actually funny because like my first interest was astronomy, and then when I was deciding what to study, it's like maybe I should do something more practical, and I chose astrophysics. And then eventually I realized that well, maybe it would actually put the bread on the table. Maybe I'd actually let's do aerospace engineering because it's at least I'm an engineer. So, but interest was always there. Actually, I was very astrophotography was something I wanted to get into it, and then life took me in a different direction. So actually, I could never really develop that hobby. So, but of course, always been very close to the space and eventually space environment. So that's pretty cool. So very happy when John asked me to join the meeting and say a few words about what we're working on. So one of the things, so that's thanks a lot, Wes, for the introduction. But besides, like my deepest know-how is in propulsion, plasma physics, but of course there is a lot of similarities with space environment, which is pretty much plasma. So it actually is very hard to find in general any uh, teaching or courses or classes that actually focus on space environment, because most of the time it's people come from all kinds of different background and then eventually develop this know-how. So put together this presentation and try to introduce it, try to present it as and comparing to also what we have on Earth. So it's really weather and climate, and so that's why we look at space climate and space weather. There's some similarities, but there's of course it's a different modeling, different approach. So yeah, let's say like what we what we look for. Let's see if we can change slide. No, doesn't move. Just sorry, second. So as many, of course, as everybody knows, and everybody, hopefully, some of you might have actually was able to witness some of the phenomena of the space environments. Of course, the most obvious is the aurora borealis. This is sometimes visible all the way to lower latitude, even in the U.S. There've been like even more recently very strong events that actually showed off pretty well. So, for example, this is one of the events that happened just in 2024 when the pretty much the sky went on fire over Minnesota, and pretty much the higher latitude of the United States. But it was such a strong event that actually we were able to visit to see it even from DC. So let's say like I'm currently in the DC area. So all the way down to Florida, well, that's tough. It would really need to be a really big event to go all the way down there. So actually, as far as I know, I don't know if that was ever visible uh, all the way to your latitude.
We got it last year, actually.
Oh, did you? Okay.
Mhm.
Did you even from just any city, or did you have to be in like in one of those dark sites?
No, we got to see it from my house even.
All right, so then it was a big one. I mean, the last couple of years we did have pretty big events. So that's I'll go a little bit in the details of like where this comes from, but this is one of the obvious results of radiation. So these are charged particles that make it all the way into the higher part of the atmosphere. And so when they start to interact, the charged particles start to interact with the higher zone. See, it's pretty much starts to light up, and different colors is different particles. So from argon to nitrogen, you start to see the different impacts. And yeah, and I'll tell you a little bit more about that. But this is just to also to show like this is let's see if this shows up. Yeah, it's kind of an actual recording of that what was a geomagnetic storm. So we have this huge event. It's obviously related to the sun, and there is this enormous ejection of material, it's plasma, all kinds of particles that travel to space, get deflected by the magnetic field of the Earth, and then get funneled into the pretty much to the poles, the magnetic poles of the of the Earth. Now, depending how intense that is, of course, it spreads. And so rather than being just concentrated around the poles, which is the much higher latitude, a few degrees off the actually geographic poles, get spread and go way more south than that. So this is just also pointed out to see, like you can see the large difference in the night sky coloring, where the intensity was, it almost looks like a huge storm going across the country. But even if the tail of that, even if not directly visible by the specific instrumentation of the NASA satellites, we went to all the way down to the lower latitudes. So to stay on that, as I mentioned, this is due to massive ejection of material from the sun. The mass ejection, of course, are related to periodic behavior of the sun, but they are not really predictable. So that's where we start to kind of draw the line between the space weather and the space climate. The climate follows much longer time scale, a bit like the seasons on Earth, while the space weather is more after the event. So it could be like like a storm on Earth. In this case, like this massive ejection of material. I always found this pretty cool image now that we have like very sophisticated observatory in space. This is the Soho. We actually record them live. We can see this happening. That's, by the way, that's a comment on the side. Who knows? Maybe some of you might have taken like lots of pictures of that when you pass by. Yeah. So that's so these events happen often, but at a different. They can be of different entities. So you can imagine these definitely have an impact on whatever is in space. As like any storm, like a ship in the middle of the sea. If it hits the storm, well, they're gonna feel it. But interesting enough, this can, as I mentioned, with the geomagnetic storm, and you see nice bright colors in the sky. Well, it's actually impacting potentially like a lot of operation even on Earth. So for sure, in space, this is it impacts satellites communication. It can impact the actual concentration of species in space. So that's what I call drag. Because it can actually change even the higher atmosphere of the Earth, as rarefied as it can be, is still has an impact on satellite operations, especially those operating really close to Earth, what's called the LEO, and the very low Earth orbit. But then this has been shown in the past. Some of these very big events actually impacted the infrastructure on Earth. So all the way down through the magnetic protection of our planet and the atmosphere, we still experience events like electric power transmission overload. There was a very big event in Canada a few years back, where pretty much the huge chunk of the western part, of the eastern part of Canada pretty much went dark. And similarly, all the systems, many of the systems that rely on communication, they can be impacted. So I found always this is pretty cool. There was this massive ejection in 2024, and actually a lot of the operation in the agriculture went down. It was like this. Like nowadays, a lot of systems are automated. They use GPS, for example, work in the fields where there's a bunch of trucks that just follow a specific path, and they're all controlled autonomously. Well, because of that event, pretty much it's because of space radiation that actually the system went down. Of course, it's a very sophisticated and complicated troubleshooting, but eventually those charges make it all the way down to system on the ground and affect the electronics. They can disrupt chips. They can actually create short circuit. They can change memory state in the devices. So there is a lot of impacts that charged particles, electrons and protons and heavy ions can create. Another, I don't have the slide, but another really interesting event that happened on Earth was at some point a miscalculation of votes in the Netherlands, and somehow the community came to the conclusion that was due to space radiation. It's because there was a specific event, and the counting machine pretty much flipped bits and changed the counting of the votes, and so somebody got elected because of space radiation. Now, in that specific case, I think it's a bit of a stretch, considering also the social implication, pretty big. Of course, they did not change the elected person because of the failure investigation, but this is just to say, like, space radiation does impact us even on a daily basis, even in our social life, and it's stuff that happens in the background, and most of the time we don't even have a clue. And as much as on Earth, you can imagine how much it's impacting the space business. So, like a big one was actually it impacted the operation of Starlink. So Starlink is this huge constellation from SpaceX, supposed to pretty much it's an internet network from space, and they have like thousands and thousands of satellites. Now, when they launch in a very low orbit, and then they get raised to the nominal orbit. Usually they get injected around 250, 300 kilometers, and they go all the way up to between 400 and 500 kilometers. Now, because of a very big event, the amount of this plasma was so high that actually it increased, it kind of lifted, it kind of blows up the atmosphere, and so it increased the density of air even at hundreds of kilometers. So it's supposed to be vacuum. Well, it's not really vacuum. There are always some particles. It does create drag, and because the drag increased, and pretty much all the whole plane of spacecraft dropped in altitude, and the propulsion that was on board it's not sufficient to actually recover it. So actually they lost all the spacecraft, which kind of had an early re-entry in the atmosphere that burned into the atmosphere. But like that, of course, the other in other cases was particles that impacting electronics. They could damage. They could damage power distribution. They could damage memory. They could damage onboard computing. Another big one, for example, is the impact on the Webb Space Telescope, which I'm sure all of you know. It's taking great pictures lately. And again, like what's called with galactic cosmic rays, which I'll go through, it impacted operation pretty much went dark for a little bit. And in that case, galactic cosmic ray is actually not produced by the sun, but I'll tell you more. Tell you more about it later. So there's definitely a lot out there. It's impacting us in our daily life. So to go a little bit more in the details of what I mean with space climate, space weather. So the sun is it's the main player in our solar system. Is the source of these energetic particles, but it's also what we call a modulator of those particles, because as much as it's one of the main sources, it's not the only source. What makes the difference between space climate and space weather is mainly the time scale. So if events happen on the matter of seconds or days, like a corona mass ejection, well, then we're talking about space weather, and that impacts, for example, space impacts launch and operation, because we do actively look for those, and if we know there is an event like that coming, you don't launch, you wait, you don't launch the spacecraft. Because it can impact the orbit, the insertion of the satellite, so it's a big impact. Instead, we speak about space climate when it goes over the whole duration of the mission, and we're talking about years, tens of years. There are missions that last for 20 years, and so radiation can impact over time, because we have what's called accumulation of dose. So particles constantly hit everything. And so time over time, you charge them up, and they can degrade parts, they can degrade materials. And so they can impact eventually the length of the mission if it's not designed properly. So when we talk about particles, we talk about protons, the sun eject protons, heavy ions. So from the sun, we get particles all the way up to iron, and then of course we also have electrons. We have plasma. So plasma is a mix of all charged particles, neutrals, electrons. It's all of them. Now, these particles are different types because they can constantly flow, or they can actually get collected over time and actually stick around Earth. It's what we call trapped. They get trapped in the magnetosphere. Protons, electrons, they can still come from the sun or from outer space, but it's different because protons, those that are trapped, are there always, and then they get modulated. So depending on events that happen on the sun, like the mass ejection or flares or change in the wind, they can change in concentration, and so the flux of those trapped particles, they can affect the spacecraft, can change over time. So since some of these words, most likely many of you already also know it, but kind of the generation of this particle comes from solar wind. Solar wind is this constant flow of plasma that comes from the sun. It's always there. The mass ejection I gave you example, and it's like just a pretty much chunk of material that get blown off from the sun, and it's because it's actually like a mass. It's electric. This was mass. It's actually material. It actually has its own magnetic field. That's why it's treated differently, because it also interacts differently. And then we have flares, which are most likely many of you might even take a picture of, which is also, it's more related to the cycle of the sun. So all of these, they do play a role with the geomagnetic storms, but then of course the biggest player is when you have this large mass of plasma, which is the CMEs. So talking about the solar cycle, many of you may know, with these a few centuries, we've been starting to look at this, and then it's very hard to predict. It's very, but it is real. It's there. It's physics. So it cycles. So we have like 11 times 2. So we go through a cycle of solar max intensity. We have more flares. We have more higher chances to have more events of CMEs. This is mainly kind of one of the way to track it is counting spots on the sun. When you start to see like these more intense areas or dark spots that go together. This kind of cycles with a solar mean when it's quieter and the sun is less active, which doesn't mean it's less radiation, it's just different radiation. And then every 11 years, the sun inverts the polarity of the magnetic field, and it behaves differently. So here's it's a plot of actual data collected. It's public data. You can get it from the NOAA website, but you never know how it's going to be the next cycle. So, for example, for modeling, we try to base our analysis on kind of worst case. So, space we like to be conservative. Now you may think, okay, so it means you're looking at the data from the 60s. Like no, actually no, because it also depends on the quality of data. So actually, the worst case that usually we look at is it's from the like late 80s. So cycle number 22 is one of those that are usually considered. Now, interesting enough, the current cycle that's showing itself as one of the most intense, maybe not as intense as the cycle 21, 22. It's getting closer to 23. But also wanted to show here, like, it's marked in with the red, and the gray is kind of the range of confidence, and it's already kind of pretty much beyond what was expected to be. So very hard to predict, but still, we're flying satellites, so it means we're still doing something right. Give a little bit more of the background of the solar wind, so it's always there, constantly operating, and we're talking about a constant flow of particles that kind of invest our planet. Likely enough, or I would say obviously, because we're here, we have a pretty strong magnetic field that is actually shielding the planet from these particles. But when these particles, so they get deflected, and actually they also shape the magnetic field of the planet. As I was mentioning, now you can see that we have these particles can make it through this sheet, the magneto sheet, and funneled into the poles. And that's what actually is creating the aurora borealis. And one thing, all these particles, as they get injected in our magnetic field, they get trapped. So it's actually particles coming from space. It's not generating from anything else, from our Earth or from anything else, come from the sun or from outer space. They get injected, and then because of pretty much the single particle motion, they get trapped. So particles are charged, so you can act on them, and they follow the magnetic field of the planet. As soon as they start to get closer to Earth, they start to have the gravity has an effect. So there is the amplitude and the wavelength of this motion change, slows down, actually stops, inverts, and gets pretty much ejected back. And so it goes back and forth along the magnetic field line of Earth. Now it's these particles, they keep going, and so that's actually what's building the heliosphere. And it's kind of on the scale of our planet, also our solar system, and the sun as its own kind of shield, which is kind of marked by the heliopause. Now, recently, just in the less than 10 years ago, we do have probes that went all the way out there and actually actively crossing. Somebody say they finally crossed, some say they're still in the middle of it. But there was something that was obviously obvious from the data collection of the Voyager probes. And that's because they have detectors of charged particles, and you can the detector were built such a way that we can differentiate from particles that are coming within the solar system versus the one actually coming from outside, and that's what we call actually the galactic cosmic ray. So and that's based on the particle type of charge, and especially the type of rays. It's like some type of rays, gamma rays, come from outer space. So we could detect, and that's kind of the other bigger contribution is what we call the GCR, the Galactic Cosmic Ray. They're always there, they're always flowing through everything and anything. But again, our sun does play a role as a modulator. So depending on the activity of the sun, the intensity of this GCR can be lower or higher, depending on the time. And so the interesting thing is that, well, who's generating this GCR, and most likely many of you might have even taken beautiful pictures, and these all come from supernovas. So actually, all the radiation, all the GCRs, and actually the heavy ions beyond pretty much iron, it's all made by the outer solar system, which I find super cool. Just pick two. I'm sure most likely you guys have pictures that are way more beautiful. But it was interesting to pick like one of the supernova that was actually it was so intense. They was such as observed by naked eye during daytime, and already like thousands of years ago. So this is just to say like these strong events, they look beautiful and look great, but actually they have an active role in our daily life. So that's why it's extremely important to keep studying space, keep studying these bodies, these events, and try to learn more, because at the end of the day, it does impact the way we live on a daily basis. And actually, the first time this was observed was actually more than 100 years ago. It was an experiment on an aerostatic balloon. It was not really meant was for that. They were looking at, of course, charged particles, but eventually, yeah, it came down to understanding that these were like due to with different charging, different behaviors, and eventually it was correlated to the GCRs. And yeah, as I said, so this is the interesting stuff, is that somebody may think, so how does the heliosphere play a role? So intuitively, somebody may think like, oh, when the solar ring is the most active, the GCR are lower, and that's because so that's pretty much what we're seeing. So it's depending on the solar cycle, we get more higher flux. So the higher the activity of the sun, and then it drops the so the flux may change, but actually the peak where of those particles is actually different. So the higher, more energetic GCR are actually during the peak, the solar max. While instead during solar mean, we have we have more flux, more particles, because they're not pushed out, but they're also they are interacting differently, and so we have like a lower energy. So if try to break down a little bit more what this radiation means. So as I say, like for all the systems, as I mentioned, so we have these trapped particle, and actually they are specific, what we call the belts, Van Allen belts, that are containing most of this particle. We have an inner and another belts, and it's mainly electrons and protons. And the way it impacts us is because these particles are always there, and so these can have an ionizing effect. They're charged, which means they can charge differently piece parts in the system, but they can also have a non-ionizing effect, meaning that they also have a mass, they have a speed, so they can strike and physically damage the lattice of a structure, or the mirror, or a lens. So whatever is actual the structure of the component, the material is critical. That's where over time can impact, and that's why also pretty much everything has a life. For example, if you imagine of solar cells, power degrades over time because eventually they get damaged by radiation. It's what we call single event effect. So these, not only these particles constantly accumulate charge, but they also, when they strike, they can hit a very specific part of the atoms. They can knock down electrons, they can interact with nucleon of elements, and so they can generate other. They can break apart structures. So this actually shows up as it's a one-off, because I mean statistically that the fact that the one particle hit another particle is extremely low, but when it happens, that's the one-off. And of course, this is also those as well. The same way it impacts hardware, it can impact people. So there is a lot of studies on International Space Station and during missions to understand, what is this radiation experience with that when you get an X-ray. So that's definitely, when you're out there, you're not as protected. So of numbers, but just to say like how energy is, just to say, we have like belt close to Earth, we mainly have protons. When instead you go farther from Earth, so let's say in geo orbit, which is mainly telecommunications, and bigger spacecraft, then you have mainly electrons, and these interact in a different way. So when you design spacecrafts, it's a totally different design. And just fun fact is, I mean, we're talking about days or week for this particle to reach Earth. So that's why observation important, because actually you can act. For example, you can turn down instrumentation or cover a mirror, so protect the hardware, or for people get in a safe area of the space station. Interestingly, so this is not very even, and so there is this area on planets called the South Atlantic anomaly, where the magnetic field does a weird thing, and because the Earth magnetic dipole is tilted compared to the Earth, we get this anomaly, which is pretty much out of the South America, where you have a very different environment radiation-wise. It's very specific, but also it impacts mainly very low orbit. I'm kind of late, so I'm gonna speed up a little bit. Then we have the non-trapped solar particles, and these are the CMEs and the solar flares. This is pretty much what we call the solar energetic particles. And those are mainly protons. So it's ion, but it's just one, the more mass one. And this again impacts to accumulating those, damaging solar cells. It can create this single event effect that can knock down and create pretty much to affect instantaneously hardware, and that could be destructive, meaning like you cannot recover from it, or it's something you could recover just by booting, or you have the correct software to just correct whatever error it may induce. But we also have the heavier ions, and this can go all the way up to uranium. And this is mainly doing a heavy ion. It's mainly impacting single event effect. It's bigger particles, a charge, so that can really it's a higher chance pretty much to strike another nucleus. And of course, this is very hazardous for people. So in this case, we're talking on the range of tens of kilo electron volts to hundreds of mega electron volts. And now we're talking about minutes. So these are much faster, more energetic. So they get they get faster. They can also penetrate deeper. And then with the GCRs, again, these are pretty much generated from supernova. Again, these can contribute to charging those. They're always there, they're always present, so they can charge up and accumulate those or damage structurally the lattice of material, which is the non-ionizing dose. It's one of the biggest stores for solar single event effect. That's because this again we're talking about heavy ions, and of course there's people. And now we're talking, as you can see, much higher energy. It's going all the way up to giga electron volt. Just fun fact about the other celestial bodies. We got the Moon and Mars, and actually they don't have a magnetic field. So interestingly enough, which means there are no trapped particles, and they're also much more exposed to all the energetic particles. So rather than have this continuous flux coming from the magnetic field itself, we just have this constant flow of GCR and SPEs. A very interesting fact, actually, Moon and Mars are very similar from that point of view. That's also one of the reasons why there's a lot of interest around Mars and preparing on Mars and building on Mars and on the Moon in order to go to Mars. So very likely the Moon will become a test bed also to understand radiation environments on Mars. And instead, the other celestial bodies, we have Jupiter, which is way bigger than anything else, 20 times bigger than Earth, the magnetic field. And as you may imagine, that also gives the chance for the trapped particles to gain and get much more energy over time. Interestingly, Saturn interacts with the moons and rings, so that makes it a very different type of environment. And from Uranus and Neptune, we have very limited data, but we do have some data thanks to the Voyager missions. And because of very different way they spin, the magnetic field is totally different thing. So there's actually currently missions they are trying to push to go study Uranus more. Very fascinating body. With that in mind, of course, we need to build a spacecraft. So there's a bunch of models out there trying to understand what's going on, how to forecast. Very important, of course, are short-term forecast, especially for human space flights when they need to plan the EVAs, the extravehicular activities. But also, if there are these massive CMEs, you're not safe even within the space station. They have like dedicated area which much higher shielding, and of course also for the assets for the other satellites. There are models that try to understand what's going on today, tomorrow, but like weather forecast on Earth. Well, I can the farther in ahead in time you go, and it's the least reliable it becomes. But then we have to do with it, and we have to deal with it, especially let's say from the space climate point of view. We do have to design satellites, and we have to live with that. So that we do have modeling more or less sophisticated. That current modeling is actually it's very accurate, but nobody wants to use it because then it would make satellites way more expensive. So there is always a trade-off between what you can build and what you want to build. So there is, by the end of the day, satellites are built, missions are successful, and so all of this is fed like any engineering exercise. Risks are evaluated and mitigations are put in place, but there is never zero risk. So when we design a satellite, we do account for all possible radiation sources and how they can impact in different way the different part of the satellite. But you know there is a trade-off. One thing that I've never mentioned in this presentation, but something that it was definitely a thing in the 60s and 70s. I don't know if it might become a thing again. It's actually human-generated radiation. So some of you might have heard about the Starfish program, where the United States pretty much detonated a nuclear weapon in space, and the impact was not much about the explosion knocking down satellites, but actually the radiation that created it knocked down a number of satellites that were exposed to that wave. So that's kind of the bullet point here. When we decide satellites, especially in commercial war, well, we ignore hostile threats, because if you start to design a satellite considering somebody can blow up a nuke in space, well, you're never going to go anywhere. Let's say it's a real thing. It's a real threat. There are meetings and conferences about that. Not too many talk about it, but it's a real thing. And so yeah, so there is definitely this another thing to be account for. For example, they be talking about sending more hardware and missions to Mars. One of the way to do it is we need a lot of power, and so, for example, is to make the mission relatively short time frame. We need a lot of power to have a lot of thrust, and so the propulsion system may actually be based on nuclear energy. So the source of the power could be nuclear, which means now you are adding a radiation source on the spacecraft. And when usually you look at things coming from outside of the satellites, well, soon we may be looking at actually radiation source coming from inside of the satellites. So that could be actually one of the more challenging aspects of designing satellites with because space radiation, well, we still call it space radiation, at the point that radiation will play a big role in that. And this is just to finish, as I was mentioning, you know, we have to deal with risk when we design, and this is just an image to show that what type. So, you know, on the bottom, on the x-axis, let's say you see all the type of sources of space environment, you know, trapped electrons, protons, solar proton, GCR. And now along the y-axis, you see the altitude, so the different type of mission, so how these particles impact in a different way the different altitudes. So the darker it is, the more the hazard. So if I look at the electrons, you need to go beyond 10 and 20, actually it's around 22,000 kilometers, where you start to have the GPS and the Galileo mission, they get heavily impacted by electrons. If you around 10,000 kilometers, when you have the O3b satellites, then it's protons that impact. It's creating the big hazard, and so forth. And so kind of at the bottom, and on the top, you start to see the actually also those what each of those can create. So electrons, protons, or protons, they contribute to ionizing dose, non-ionizing dose, surface effects, spacecraft charging, and so forth. So this is just a visual to say like it's a very complicated picture of how this radiation can impact the different type of mission, the different altitudes in different ways. So, and that's the kind of thing we always have to deal with when designing the spacecraft. And with that, I thank you all, and I hope this was informative. If you have any curiosity or question, I hope I can answer. I don't promise I can answer.
Nice. Thank you so much, Giovanni. We did have a couple questions just come in. Frank Kane asks, given what you know about solar particles and GCRs, would you go to Mars?
So you might have seen a lot of animation and things that people look at bases and they want to build them underground. That's one of the reasons is to have shielding. So it's definitely a threat. Now, can you live long term on Mars? Well, we don't know because studies are still limited. It's based on what we know from the space station. So that's also one of the reasons people want to do more a permanent base on the moon, so you can keep studying this stuff. Can you create a colony, 1 million people on Mars, and live on the ground? Yeah, that's a tough one. Most likely, might would be an underground. So I'm sure many of you know Total Recall. It might not be much different from that.
Yeah. A follow-up question from Frank is anyone thinking about radiation shielding and hardening for all the proposed AI data centers in space?
Yeah, no, that's definitely it's definitely a thing. So the one thing about that is that parts that are radiation tolerant or rather hard, right now it's kind of very expensive because they're very limited. So there is a bit of the discussion where, well, the moment you actually produce there is mass scale, mass production. So it's all about the design. So if you design it correctly, of course, I mean, you could contain costs and still make it. Otherwise, there is more the brute force when you actually add external shielding, which is not very efficient from a design point of view, but that's the other solution. Different materials can protect in different ways. So external shielding is also a way to correct that. And then redundancy. So you have all of these, you can have redundancy as long as it doesn't last too long, that's also a way to solve the problem.
John Pinto asks, can you describe how the polarity of the magnetic fields on the sun are measured? Are certain polarities associated with where the magnetic fields are located on the sun?
Yeah, I think it's I'm not able to go into details, but it's definitely based on the observation of the spots, and I think also the last mission, the the polar probe that went to one mission actually went all the way to the sun, pretty much touching the other atmosphere of the sun. So yeah, it's based on I don't know the details of the instrument. Definitely be interesting thing to look into, but it's based on tracking how the spot change, so those cycles, and the type of particles that you're getting, and how also all those particles are interacting with the instrument on the spacecrafts. It is measured. Sorry, I'm not able to explain exactly how.
What shielding would be, Bill Castro asks, what shielding would be used for humans on a mission to Mars? I think he's talking about like on the actual ship along the way.
Yeah, I mean, actually, aluminum is a very effective material to shield. So that's usually because it also offers
Did we lose you, Giovanni? Hello? I'm not lost, am I? No, I'm good. Uh-oh. We might have lost. Oh, there he goes. Okay. Well, maybe it was a solar storm. He got hit by a CME and was taken offline. Who knows? Well, uh, if he doesn't come back, Giovanni Lenguito, thank you so much for joining us, and that was a really awesome, interesting, and awesome talk on space weather. That was pretty cool.
Yeah, sorry, dropped for a
Oh, there you
second.
are. Redundancy.
But yeah, sorry, I was saying just saying like so yeah, there are definitely like dense material and lighter material used for different reasons. So the most effective way is actually to use different type of materials in order to be able to shield all kinds of particles. So it will end up being kind of a sandwich.
I had heard once that there was talk about using layers of water. So would like a sandwich of like water and aluminum, would that be a good way to shield, or is that not feasible to like have that much material around?
Yeah, that's definitely another way. It's not as effective with all type of particles, but actually water is used to even on some experiments on Earth to slow down very small particles, so that you can actually them. Uh, but also what people look at is which material am I going to find where I'm going? So let's say
Wow.
Moon, Mars, we know there is water, so it's one of the materials. So if I can use it in a smart way, why not? Because you can always think like I need water, so I need a reservoir somewhere anyway. So why just not to put it on top of our structure and just protecting us too? So people are thinking all kinds of solutions.
Uh, Bill Castro asked a follow-up question. Are you working on anything with NASA at the moment?
Not right now. I did work with NASA my previous job. It was actually one of the deep space missions. It was actually the first time we also had to look at these different radiation issues because now we're leaving the solar the Earth system. But right now, I work for Airbus US, and there are studies, but no, we don't have anything ongoing with NASA.
We've got some good questions coming in. Jason Cochran, I realize you may not be allowed to talk about JetBlue 1230 specifically due to your job, but can you talk about high level and generically about the effect of space weather and bit flips on automated flight control systems and the kinds of things software engineers need to consider to prevent incidents?
That's it's a big deal because actually software is one of the mitigation. So especially, for example, was bit flip.
Yeah,
That's one type of single event effect because it's pretty much it's one particle. It's just one particle hitting the spot on the memory and flipping the bit.
yeah.
So, and that's why software becomes critical because ideally you have redundancy. So, hopefully, the same information is stored multiple times. The software is able to constantly cycle and check if anything is off order and then doing voting. So, correct it. Um, so, yeah, the bit flip is usually the type of thing that it's the one that if you want to have some sort of single event effect, is the one you want because it's the one you can correct. Instead, there are like some other events called latch ups where the particle strikes and actually can create a short. And so there is like a thermal runaway where there is pretty much this part is just now providing or drawing more current to the point that it fails the parts. And at that point, if you look it under an scanning electron microscope, you see it's pretty much just blown off and burned out. Um, yeah, so that's definitely software is there's always a lot of work together between hardware engineer, so the actually the electronics device engineer, the software engineer, and the radiation engineer. So I would play the role of the radiation engineer, telling you like, oh, you can have all these kind of bad things. Be aware. And then the software engineer starts to think, okay, let's see how can we fix that? How can we prevent or correct, so forth. But there are very standard way to do it. There are kind of in industry standard.
Last question I think we have here. Ryan Roop says, what is the likelihood of another Carrington event, and what are your thoughts on how that would affect us in today's world with all the technology?
It would be bad.
Yeah.
So for those who doesn't know, the Carrington event is one of the biggest ever observed in the late 19th century. I think it was 1890 or something, and 92 by the late 19th century. And it was almost pretty much people were almost able to see the sun event in the horizon. So there was that obvious. As I mentioned, like the events we already showed already impact us by knocking down systems, power infrastructures. So the good thing is that it will not impact everywhere on Earth in the same way. On Earth, we're fairly protected anyway. Even if they make it, it would still be single event effect, and so that's would be just a one-off. At the end of the day, particles is pretty spread. The atoms are pretty spread. So before it's that it actually knocks down everything, no, that's not going to happen, and there is a lot of redundancy. So on Earth, we're very well protected. System in space, yes, they can definitely be heavily damaged. But again, it's called single event effect. It doesn't mean it's going to happen in the same way on everything. It can impact life of systems. It could reduce it a bit, but also again, these are very limited in time. So there is this shower of things, but then it passes. So definitely, that's it can be impactful, but it would not be, the end of everything.
Yeah, it's over dramatized. Yeah.
It can definitely happen. So absolutely, yes.
Cool. Okay, that was the last question. So, Giovanni, thank you so much for your talk tonight. That was very interesting. That was a very good talk on space weather. It was very cool. Thank you so much for being with us tonight. Feel free to stick around if you want to catch up on our club news and our astro photos.
Appreciate it. Thanks a lot for reminding me. Have a good one.
Thank you. Okay. All right. On to hopefully, yes, club news. There we go. Club news. We do have a couple more Geneva Dark Sky Nights coming up the rest of this season. As you guys probably know, living here in Florida, we're kind of going into our astronomy hibernation here in the summer. With clouds are coming in, and it just sort of stinks when it comes to observing and photography. But we're going to try on June 5th, June 6th. We are going to try to have a Geneva Dark Sky Night, and again on June 12th and June 13th, if weather permitting. So be sure to keep an eye on groups.io. And any announcements are usually 1 to 2 days in advance because we're checking the weather. We're constantly keeping an eye on it. And if we can have it, even if it's sort of spotty, maybe we'll see a star or two. We often have it on these last couple ones. So keep an eye on our announcements. Our remote sea star is often available if it's dark. If it's cloudy here in Florida, it might not be cloudy out in Texas. So be sure to get on our subgroup on groups.io and reach out to our group there. Pete Lefebvre will be the guy you talk to. He'll get you up and running in no time to use our sea star out there and get some imaging done in a dark and hopefully clear sky. Also, I want to welcome our new vice president, Isabel Chauffeton. She, as you know, stepped into the shoes of Sharifa, who went to do cool and awesome things with NASA. So thank you so much to Isabel for stepping up and being acting VP for the rest of Sharifa's term. So thank you so much, and we're all really looking forward to working with you. Also, welcome to our new board member at large, number 1, Chris Hunt. He's also stepped up to replace John Frank. Chris, as you know, is a regular out at our Geneva nights, so be sure to shake his hand and congratulate him if you happen to see him out there. Thank you, Chris, also for stepping up. I appreciate it. Again, another plug for groups.io. If you are an old or new member, please get on there, create your login, get on there and check out our announcements, the calendar, the community. It's where a lot of the things going on in the club are discussed and posted. So get on there. Again, our loaner program, we have a lot of cool stuff in the loaner program. We have some sea stars, some cool mounts, some cool telescopes. So if you are new or experienced in the hobby and want to try out a new piece of equipment before you buy anything, be sure to reach out to Paul Morrow, our loaner program chair at loaners@cfas.org, and he'll help you out with what we've got and what might work out for you. We also, with the help of John Sasson and Rob Fleming, we have the mentor program starting. There's a forum on our website where if you have questions or want to get some mentorship on a certain aspect of astronomy, you can sign up there, and somebody more experienced in the club should be able to help you out. Also, if you are an experienced astronomer in astrophotography, visual sketching, anything in our hobby here, reach out to us and join the mentorship program so that you can help others in the club. Upcoming outreach events. It's grinding down here, as you know, because the summer and clouds, but we do have a few coming up. On May 22nd, we have the Cornerstones Family Fun event. That's just this Friday, I believe. On May 30th, we have the Science Night Live at the Orlando Science Center. That's always a fun one for folks. June 5th, 12th, 19th, and 26th, we have the Stargazing with Summer Campers out at Fort Christmas. I'm hoping to get out to one of those myself because I think that one will be fun. As you know, I plug this every time during our meetings. Outreach is a fun thing to do. If you have your own scope, be sure to join in on one of these, and it's very rewarding. Having your telescope set up and showing a little girl or an old lady or whoever Saturn or Jupiter or a star cluster for the first time, you get that wow factor from them. The oohs and ahs are very rewarding. I highly recommend it. So if you at all have an interest in sharing your hobby and passion with the public, hop on our groups.io subgroup there on outreach and reach out to Doug Woods, our outreach chair, to let him know. Of course, also to our new members, be sure to read your Welcome to the Central Florida Astronomical Society letter. It explains how to get onto groups.io. It also explains a lot of your member benefits. And anybody in the club, if you have any questions, concerns, or want to let the board know something, be sure to reach out to our board members at large, Chris Hunt and Denise Woody at bml1@cfas.org or bml2@cfas.org, or to me, president@cfas.org. As usual, the board could always use some help. So the outreach committee always needs help. Doug is at so many events throughout the year, and I know you could use a hand. So reach out to him at outreach@cfas.org, and I'm sure he would welcome any assistance. We also are still looking for a programs chair. If you are at all interested in trying to put together or reach out to potential speakers for these meetings that we have every month, we could sure use a hand there. The programs chair has been open for a little bit, and we could use some help. Any committee really could use a helping hand. If you at all want to have a hand in helping the club, provide assistance, be here, be there, be everywhere, be sure to reach out to us. There is a committee on the board that could use you, I promise. So events, programs, outreach, treasurer, loaners, science, website, membership, observing, education, sponsorship, or make your own. Any of those could use the help. So any of those interesting to you, please reach out to us. Mentors, as I mentioned before, we could use more mentors for the mentorship program, so reach out there if you have any specialty, and any are welcome. And so, any of that sound good to you? Be sure to reach out to us at to one of our BMALs or to me, president at cfas.org, and that would be much appreciated. As you know, also, we are a tax-deductible nonprofit organization, so any donations are tax-deductible. We're a 501c3 organization. We're always seeking sponsorships and corporate donations, and we are on cyber grants. So major corporations like Disney and other employers often do donation matching. Coming up on astronomical events, Jupiter is on its way out. So if you haven't somehow gotten through the season without going and looking at Jupiter, please do so. I think it's down to about 45, 46 degrees when the sun sets, and it's going away quick. So I think by the end of the month here, it might not be very visible. May 16th, a couple of days ago, was the new moon. So we do have some quite dark skies right now. So if it's clear, it'd be nice and dark for you to get out there and observe. May 31st is the next full moon. It's also a blue moon. So that's going to be, it's coming back in a couple weeks. June 8th and 9th, Jupiter and Venus are going to be very close together. If you have a reasonably wide eyepiece or a reasonably small, not too big telescope, you should be able to view both of them in the same view or with a potential camera. June 15th is the next new moon right after that. And then also on June 15th, Mercury will be at its greatest elongation in the evening. So if you happen to be able to see whatever it is, 8 to 10 degrees up off the horizon, you should be able to catch Mercury. And then the next night after that, the Mercury and the moon will be very close together, kind of like it was back in February. And then finally, June 17th, the Venus and the moon are also going to be very close together in a nice photogenic sort of way. All right, next up for the last thing of our evening is the astrophotography showcase. Let's get on with that. Jeff Mirek, I think I saw you in the list. Are you here?
Yes, I'm here. You
There
hear
we
me?
go.
Yeah.
You tossed us a few cool little ring galaxies.
Yeah, two ring galaxies. There are actually several up there, maybe 20 to 30 ring galaxies up there, but they're not too common. Um, and I've been able to image three of them, and my goal is to image as many as I can. But this is a good one. Op 141 that I imaged late last year. There hasn't been many clear nights this year so far,
Oh, there
unfortunately, as
wasn't.
you are aware of. So I haven't been out too much. But anyway, yeah, this is in the constellation. I can't even pronounce it. Camelopardalis. I don't know.
I'll take it.
It's 130 million light years and a magnitude of 13.2. Um, and so the ring comes from many, I mean, there's many possibilities, instabilities, in the gas, collision between two galaxies. The ones I imaged are collisions between two galaxies, which forms a dynamic that somehow forms the ring. And many times, the young stars are out there in the outside, and the older stars in the inner core.
Yeah.
Okay, next. Another ring galaxy. This is more distant, 1 billion light years away, and I guess this was magnitude 16. This is about 4 hours of integration time. Um, and Again, this is the images I have been focusing on has been the interaction between two galaxies, and that's the principle how this ring formed. This is in the constellation Sidus. Um, and so yeah, that's that. Yeah.
Nice. I've noticed that you often submit these little, like, off the beaten path galaxies. Are you putting together a little portfolio of the lesser knowns? Is there going to be like a big, grid of images of the lesser known ones?
That's what I would like to do, and because I have been doing the lesser imaged galaxies. I mean, who images ring galaxies? Hardly
Yeah.
anybody,
Yeah.
nobody.
I'm always
Uh,
excited when you send one in, so it's very cool.
so I quite going after the difficult and the faint galaxies, and I've been pretty successful of doing that in my backyard with the light polluted areas. And still, I can bring out a lot of detail in these objects. Uh,
Absolutely.
if there's more clear nights, yeah, I can start imaging more, but unfortunately, there's not many, so I'm stuck.
Yep, that's I feel you. Well, thank you so much, Jeff. I appreciate
Okay,
the submissions.
okay.
Frank, I know you're here.
I am. Hello.
Hey, welcome from California. There you
Yes.
go.
Ah, yes. The Whirlpool Galaxy. Yeah, M51 brought out some tidal streams there that I've never seen before, which is pretty cool. So a little bit more detail on sort of the extents of the aftermath of its interaction there with its neighbor. And this is 120 hours of exposure time, which sounds cool, except 100 hours of that was completely wasted. So I was trying to capture a really faint hydrogen feature just next to this called the hydrogen cliffs. And I've seen really, really long exposures of like 400 hours to pick it up. So I thought maybe I could at least get a glimpse of it. But as we learned last month, to do that, you need really, really, really long sub exposures. When you have dark skies like this, you don't think about read noise too much in the suburbs, but out here it's an actual problem. So
Yeah.
to swamp the read noise, as they say, I would need to have more like half-hour subs to actually pick that up. So if the clouds ever part in Texas, which is where this is taken from Starfront, I'm going to try it again and see if I can start to pick up a hint of it with those half-hour subs.
Nice, nice. And what scope was this taken with? An Esprit 120 or something like that?
This is an astrophysics Gran Turismo 130
Oh,
GTX.
that's right. That's
Yeah,
right.
on a
Cool.
mighty mount, which has issues at this particular part of the sky. It has this crosstalk issue, so it's been a battle to get that working, but that's another story for another time.
Yeah. Still, 120 hours. That's probably one of the longest integration times I've ever seen by one person. So very cool. Even if it was, you didn't get what you were after, it's still very cool.
Well, try again, dang it. All
Yeah,
right,
just add to it. That's the cool part. You just keep
yep,
adding. Well, thank you, Frank.
thanks.
Chris, you here?
Yeah, can you hear me?
Yes, sir.
Yeah, so I bought a book and started reading it. When the skies are cloudy, I get in there and read a good book. And I think Bill Castro actually turned me on to this book. I bought it on Amazon, started reading it, and started doing some sketching. So I hope you picked a couple. I know I sent you a bunch. So the book kind of guided me through these, and these are the one on the left there is one that I took from the book and just kind of went step by step and followed their instructions, and they give you a little more detail. And these are actually kind of hard to photograph. And they don't come out that great. The one on the right is from a photo that I took, and I figured I'd just keep on going and do that. And so once you get the detail kind of going on the sketch, you could go out to the eyepiece and start doing the sketching. And that's what I did. And every time I did, I just got better and better, and I really got into it.
Nice.
And I don't know if did you have another?
I put
Uh,
them all in here.
oh, okay. Yeah, you could just kind of skip through some of those. I mean, that's really like at the beginning when I first started doing that back on the 4th. And if you go to the next few there,
I
you
put
could
I put them
see,
in date order. I think you had here. So
yeah, yeah, and those are at the eyepiece. And then if you look at the one on the bottom right, I started to get more detail and look and find more detail with my eye, little festoons and all those little fine lines and on Jupiter and the South Pole. And I felt like I was getting better at just doing observing through the eyepiece. Because I like to do planetary photography, and when you do that, the sky conditions have to be absolutely perfect to get a
mhm.
good shot, a good image. And when it's not so perfect out, you can get out there and just do a little sketching and just do some observing. And I found it was a lot easier, and it was a little more involved than I thought. It was really kind of fun to do. So I'm still reading the book and I'm still doing it. Did you get any other sketches that I sent you?
I
What
think that
else did I
was
send?
I think I
That was
put
it.
all I put them
Oh,
all
okay.
on here. Yeah.
Okay. Yeah, and that's it. It just, when you do sketches, I think it helps you become a better observer,
That's probably true. Yeah.
picking up more fine detail.
Yeah. And you're waiting, you can better keep an eye on how the seeing bounces in and out and catching those finer details and translating them even if they're not there very long.
Yeah, yeah.
Yeah, maybe we'll have you do a breakout session on sketching at some point in time or something like that. That would be cool.
I'm just learning. I just started. We'll see how it goes.
Well, thanks, Chris. It's a cool aspect of the hobby to pick up. That's neat.
Yeah, yeah. It's a hobby within a hobby.
Yep. I threw a couple of mine in here since as everybody talked about, it's been cloudy, so I tossed a couple of my old ones in here. This is M24 and some of the Galactic Core from last year. I took this in October. So this actually has M24, M17, M18, and I think it has a chunk of M23 off in some corner. But this is the center there is the Sagittarius star cloud, which is a kind of a view into the central region of our galaxy, just to show you, like, there's a lot of stars. um, when I show this to friends and family, people really are taken aback by, like, oh my God, stars. So I just wanted to share this one with the club because, like, there's just a ton going on in this one. If you look at it on, like, Sky Safari, there's like little annotations of objects all over the place. This next one is M74. I also took this one back in October. Both of these were taken at Chiefland, and this is your pretty typical spiral galaxy, and it turned out pretty good. And some of the little background stuff is pretty pretty detailed there. So I liked this one. I thought it came out pretty well. All right. Next up, Luke. I think you're here. Yeah. Oh, I think that's right. You mentioned in your email you wouldn't be able to. You don't have a microphone. So Luke submitted this C-star image of Andromeda. So not a bad image of Andromeda with M32 and M. I don't know if M110 is there. Yep, maybe not. But yeah, M31 is shining in all its glory there. So thanks, Luke, for this submission. I appreciate it. Pete, at the buzzer, if you're here.
Yeah,
Yeah,
I'm here.
you submitted your final version of this, I think, and I saw it during the presentation, so I did nab it and throw it in here for you.
Oh, great. Thanks. Yeah. So, I mean, I started with the C star to do a lot of mosaic uh, images. So this represents about 7 hours of mosaic data. The pretty typical M81, M82, and then NGC 3077, I believe. But given our C stars and alt-az mode, the nice thing about mosaics is if you get enough subframes, you can do away with the field rotation. So this is about 7 hours, but we get some more clear nights. I plan to, anytime the telescope is idle, to keep, long as they're seeable, to keep building some data on these objects. But you get a reasonably good image, and takes a lot more subframes with mosaic mode, but it works out really nice to get wider fields.
Yeah, this one looks great, and if I'm not wrong, I'm pretty sure there's some IFN there just off up and to the left from M81 itself. There's that little loop of IFN right there, and that with a C star, that's darn impressive. That's pretty cool.
Yeah, I kept trying to hope I could get some of that in there, but I think with get double the subframes, we may be able to see a little bit more of that without, overdoing it in
This
the
this time next year,
processing.
probably, right?
Yeah. Yeah.
Just keep adding. That's the cool thing.
Yeah. Yeah.
So if anybody, again, if anybody's here watching this, this was taken with our Sea Star that's out at Starfront in Texas. So if you are in the club and want to get some time on a dark sky telescope, that's where this is the kind of image that that thing can do. It's out in a very Bortle 1 dark sky, something that most of us don't have access to. So if you get a chance, take advantage of that. Cool. Thanks, Pete. Always appreciate that one.
Yep. Sure thing.
And I think, yep. And that'll do it for tonight, guys. Thanks everybody for sticking with us tonight. And again, thank you to Giovanni for his awesome presentation on space weather and climatology. I really appreciate it. And to all of you out there looking to do any observing or astrophotography, don't be picky. It's cloudy right now, so if you get a chance, if there's a peak in the clouds, take advantage. And I'll see all of you next time, and clear skies.